Hey everyone, I just wanted to finish up the last few slides from chapter 1 for you before we begin chapter 2 next week. So here we go. Okay, so last time we looked at the example of a viscous fluid in a gap between two flat plates and calculated the shear stress. This time we're looking at the flow also between two flat parallel plates, but this time both plates are fixed. Neither one is moving, and the flow is happening because of a pressure difference. So we're given the velocity distribution between the plates. It's here. This time, y equals 0 at the midline, and the mean velocity is capital V, and h is the half height of the channel. Right? So now we need to determine the shear stress on the bottom wall and the shear stress acting on a plane parallel to the walls and passing through the center line. So this mid-plane here. Okay. So again, we're going to assume that this is a Newtonian fluid because there's no reason not to. And so for a Newtonian fluid, we've got this equation here. So we can actually go ahead and begin to just calculate the derivative here. So this is our expression for u. So then du dy is minus 3 capital V y over h squared. And if you work that out for yourself, you'll see that that's the case. So for A, along the bottom wall, y is equal to minus h. So there, du dy is 3v over h. Okay, so now if we plug that in to our expression, tau is equal to mu 3v over h. And we go ahead and plug in the numbers that were given for that, 0.04 pound second per feet squared times 3 times 2 feet per second over 0.2 inches. But of course, we have to convert between feet and inches for dimensional consistency. And we get that it's 14.4 pounds per feet squared. All right, so that's the shear stress developed on the bottom wall. What about in this mid-plane here? So in the mid-plane, y is equal to 0. And this means that du dy is 0 here, right? If we look at the expression for du dy, and that means that the shear stress is 0 there as well. All right, moving on to the next slide here. I want to talk about compressibility in fluids. So I'm not able to play it right now, but if you go ahead into your e-textbook, you can play video 1.7. What it shows is that if you have a balloon and you fill it with some water and you squeeze the balloon, right, you're not able to compress the water. The water just sort of squishes around in the balloon and goes and makes different pockets, right? But the volume of the water stays the same. So, and that's really to make the point that water is not compressible. And in general, liquids are not very compressible, but gases are. So let's talk about this concept of the bulk modulus. Let's write it down. The bulk modulus E nu is equal to minus dP over dV over V, or dP over d rho over rho, where P is the pressure in the fluid, V is the volume, and we've got our old friend rho, the density. And what is this really saying? The bulk modulus really tells us if we apply a small differential pressure to a volume of fluid, what's the change in volume of the fluid that results, right? So if you have to apply a large amount to get a very small change in volume, you have a very different bulk modulus than if you only have to apply a small amount of pressure to get a large change in volume. And this can also be expressed in terms of the density instead of the volume. Now, if we're talking about gases, then we've got something called the ideal gas law, right? And you see it here. And this only applies to gases and only certain gases. You can read about that in the textbook. And here we've got the pressure P, we've got the density rho, we've got something R, which is the gas constant, and that's different for every gas. And then we've got T, which is the temperature. And I just want to talk about a couple of special cases. If we have an isothermal process, then we can assume that the pressure over the density is a constant. And we can derive that the bulk modulus is equal to the pressure in this case. If we have an isentropic process, that means that something, compression or some other process in the fluid, is happening with no losses, without entropy, no heat exchange with the surroundings. Then similarly, the quantity P over rho to the exponent K is a constant, and the bulk modulus is K times P. And a couple of things to note here. When we deal with the ideal gas law, it's important to have absolute temperature and absolute pressure. So that's a common way to make a mistake when you're calculating using that equation. And I'll just mention this ratio of specific heats that you may remember from thermodynamics. Right, and that's our K, or exponent K over here. And when we're thinking about the ideal gas constant, you're going to want to be referring to tables 1.7 and 1.8, which give the properties of common gases. They tabulate the gas constant. All right, moving on to an example. So here we've got compressed air tank with a given volume, and it tells us that the temperature is 70 degrees Fahrenheit, and the atmospheric pressure is 14.7 psi. So when the tank is filled with air at a gauge pressure of 50 psi, determine the density of the air and the weight of the air in the tank. So a couple of things here. A gauge pressure, so this is a really important concept. So if we have a pressure, any pressure that's given, we need to find out if it's absolute or gauge. And the absolute pressure is equal to the atmospheric pressure plus the gauge pressure. Okay, and that's always true. So you need to figure out if you're given a pressure, whether it's absolute or gauge. If it's gauge, you may need to add atmospheric pressure to it. Okay, so we can determine the density from the ideal gas law. So rho is P over RT. And here we've got 50 pounds per square inch plus, now it's told us that 50 pounds per square inch was a gauge pressure, so we need to add atmospheric pressure to get the absolute pressure because we always need absolute pressure and temperature in the ideal gas law. So we're adding that 14.7 pounds per square inch. We're using our conversion factor between feet and inches. We're going to tables 1.7, 1.8 and looking up the gas constant R for air. And finally, we're taking that 70 degrees Fahrenheit that they were given and adding 460 to get absolute temperature in degrees Rankine. And this gives us 0.0102 slugs per cubic feet. All right, so that's our density. And we were also asked for the weight. So the weight is going to be equal to the density times the gravitational constant times the volume. So that's what we just calculated. Times 32.2 feet per second squared times 0.84 cubic feet. And we end up with 0.276 slugs times feet per second squared, which is just the same as a pound. So it's 0.276 pounds. All right. Save that and move on to our next slide. So I want to talk about surface tension. I've left this link to one of your homework 1 assignments done. It's a great example. It's a razor blade floating on the surface of water, which it shouldn't be able to do because the razor blade is denser than water, but it can because of surface tension. So surface tension is a force that develops at the interface of a liquid and a gas, so commonly water and air. And it's proportional to length, not area or volume. So for example, if we take a liquid droplet, and hold on, I'm just gonna plug my laptop in here because it's giving me a low battery signal. If we take a liquid droplet like you see here, and we cut it in half, you have to imagine that, right? Because you can't really just cut a droplet in half and have that hemisphere shape, but imagine we could. It would look like this, and you'd have some pressure on the inside of the droplet and some at the exterior of the droplet, and you'd have this surface tension force developed around the perimeter and denoted by sigma. So surface tension, we denote by sigma. It has units of force per length. For example, newtons per meter. If we look at this droplet example, we've cut this droplet in half. We want to find out the pressure difference inside and outside the droplet. So we can sum the forces in their x direction, set them equal to 0. And we get that the change in pressure times the surface area of this cut droplet surface is equal to 2 pi r sigma, right? We've got the perimeter and then the surface tension force. So we can rearrange and get that delta P at the internal minus P external is equal to 2 sigma over R. All right, moving right along. No, actually, that's the last slide I have for you. So that finishes up introduction of topics from chapter 1. You can go to Hyungan's lecture today where he'll do lots of examples from chapter 1 in preparation for homework 2, and we will see you next week. Thank you.